Hello, this is Matteo Torrejon, and welcome to Lab 6, Faraday's Law, for PHYS 2212. So, for introduction and purpose, in our experiment, we wanted to study the strength of induced currents to slow down a bar magnet going down a tube surrounded by aluminum foil. We were able to quantify what we saw through our observational data and the data we were able to get from GlowScript. Our results were that our system was the bar magnet and aluminum tube. The surrounding was everything else, and our observational data was we found that the bar magnet fell down the tube for 1.26 seconds, and our computation found that it was 0.783 seconds. So for main physics ideas, first we have the Faraday's law, and this law states that when one changes the magnetic field through a loop, it causes a magnetic flux through the loop, and this can induce a current in the loop. Lenz's law is the law that is represented with a negative sign in Faraday's law to demonstrate that the induced current in the loop opposes the change in the magnetic flux that is first experienced in the loop. And our Beer-Savart law is the law that allows us to find a relationship between a magnetic field and a constant electric field, and that a moving particle/current can produce a magnetic field. So if, in this example with Faraday's law and Lenz's law, if the magnetic field goes through one direction, then the induced current goes in the other direction of the magnetic flux to oppose the change in that magnetic flux first experienced in the loop. So in setting up our experiment, our first step was to collect our observational data. We did this by dropping a strong bar magnet through a column or a tube of aluminum foil. When we dropped the magnet through the aluminum foil tube, it caused a change in the magnetic flux, which induced an opposing current in the aluminum foil tube, which slowed down the travel of the magnet through the tube. We recorded the time it took for the magnet to drop down through the tube, and then we simulated the drop in GlowScript. And we did this around 5 times. And so this is the data that we got from our experiments, where we first started at around 0.38 seconds. We dropped it. We stopped at 1.55 seconds. We found that there was a time of 1.17 seconds. And we did this for steps 2, 3, 4, and 5, where a second step we found that the time to drop was 1.23 seconds, the third step was 1.23 seconds, the fourth part was 1.19 seconds, and the fifth part was 1.39 seconds. And so this was our computational model in GlowScript. We edited the code first in step 2 to the edit and create a function to calculate the magnetic field of the bar magnet. Then we edited to create a function to calculate the magnetic flux, where we calculated the flux dt through each ring due to the falling magnet. Then we edited the line to calculate the gravitational force on the magnet, computing the flux dt for a ring due to the falling magnet, and then we edited another line to calculate the current in the ring. Then for steps 5 and 6, we edited the next 4 lines to compute the typical B field at each ring. And then finally we calculated the magnetic force on the magnet to calculate the net force on the magnet, and then for the next 2 lines we updated the magnet's velocity and position to get our results in the next slide. And so these are our computational model results, where we can get a great visualization of what really happened. So on the left we can see visualization of our bar magnet falling through our aluminum foil tube, where the blue part at the bottom is our bar magnet after it has fallen. But the right side really allows us to see what happened, where our velocity versus time graph, we can see the velocity on the y-axis and the time on the x-axis, that over time the velocity sort of curves out into sort of almost constant, because the induced current in the aluminum foil creates an opposing force of that of the falling bar magnet, which slows down the speed of the bar magnet, and that is why your velocity curves out. So what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So according to Ohm's law, decreasing the resistivity would increase the strength of the opposing induced current in the tube. This would result in the bar magnet moving very slowly through the aluminum tube. And what if holes or slots were cut into the tube? How would this affect the ring currents in your model? There would be less rings of current through the tube, and this would result in a much weaker opposing magnetic field, causing the bar magnet to move through the tube at a much faster rate. And then for errors, there were likely errors with our time measurements, as there was a good chance that we did not get our time measurements correctly due to human error. Finally, for air resistance, we assumed that there was no air resistance in our model. And then finally, friction, we also did not consider whether the bar magnet could have hit the sides of the tube, potentially causing friction and slowing down the bar magnet even more. Thank you.